Okay, so today we're going to change our gear a little bit from unsupervised learning to supervised learning. Recall that we have talked about two types of unsupervised learning. One is clustering, and for clustering, we talk about algorithm-based clustering, including k-means and hierarchical clustering. And we also talk about model-based clustering, which is based on a probabilistic model. So for that, we talk about the Gaussian mixture model and the related EM algorithm for estimating the parameters in those probabilistic model with latent variables. Then we move on to talk about dimension reduction, and we talk about several techniques in the past two lectures. So today we're going to talk about supervised learning, which is something people also use in bioinformatics, although they may not use this as often as unsupervised learning, because usually we do not have very well-defined labels. So let me start from the beginning. So the GLM and the LMM, so this stands for Generalized Linear Model, and LMM stands for Linear Mixed Effect Model. So these two are both types of supervised learning. And they are very different from what people now use a lot in their research or in social media, the deep learning. Deep learning is also a supervised learning technique, but I would call this GLM and LMM the classical part, which focuses more on interpreting parameters in the model, while deep learning and a lot of similar, I wouldn't say similar purposed machine learning algorithms, including random forest, if you have heard of, and the support vector machine. Probably support vector machine, I'll leave it out. But random forest and deep learning, deep neural networks, they belong to the type of supervised learning algorithms where we focus a lot on the prediction accuracy instead of model interpretation. So you see there are two extremes in this whole spectrum. So I would say if you want to go for interpretability, and another dimension you want to look at, probably I'll just do a graph. So the upper part means you have better interpretability. And if I draw another one for the prediction, or yeah, I will say prediction is the other criteria. And we're going to give you the definition formally later. So I would say deep learning should be somewhere here. So it's very good at prediction, but not good for interpretation. While for our GLM and LMM, probably they lie somewhere here. Okay, so you can have very good interpretability, but the prediction is not its strength. So sometimes, yeah, you may do a reasonably good job with some data sets, but that's also not guaranteed because your goal is for interpretation, less for prediction. Another consideration is if you have a sample size, so number of observations. So if you have n small, usually if you have small n, you may go for, maybe I should draw a third dimension. Okay, so if I draw the sample size from small to large, so then we would always prefer simpler models if our sample size is small, okay? While if you have very large sample size, you may afford a more complicated model like deep learning. So from this distinction, we can see that these models actually have different application domains depending on the data set you have and the analysis goal. So this is about your goal. And this is about the data you have, okay? So sample size is just like the budget, and the model complexity is just like your the price you can pay. If you have a large budget, then you can afford a more expensive model, but otherwise you need to stay with a cheap model. So I would say that the complexity, model complexity, also changes in the same way. So we need to be very clear that there is no single the best model for all tasks. There's no answer to that. It's always case by case. And that's the reason why we need to learn this class, right? Why what we need to learn data science or statistics instead of just going for neural network, right? Now, there are many good packages you can use for coding a neural network, but still we need more beyond just coding. So we need to have some understanding about the relative advantages and disadvantages of these supervised learning approaches. Okay, so now I'm going to make a distinction about what do we mean by prediction and what do we mean by interpretability. So the setup is this. So for supervised learning, we have again n data points, and we just write them out. We call them feature vectors. So each data point has p features. We also have the corresponding response or outcomes. So this is usually a scalar, one-dimensional real values. So this is the response or outcome. Recall that in our previous unsupervised learning, we only have the feature vectors, and the matrix we are familiar with. In statistics, this is called the design matrix. This is the matrix on which we perform the PCA. And this is just obtained by stacking the observations, their feature vectors by row. So you're going to have X1 transpose, because by default, a vector is a column vector. To stack it by row, we just rotate it to transpose to make it a row and stack them horizontally. So you see, as a result, this design matrix is M by P. Okay? That's the design matrix, and this is the data. And so for supervised learning, what we want to learn is to find a function. You know, mathematically, a function is a map. So let's say that we call it f. This f maps from the p-dimensional space to the one-dimensional space. So here I'm going to write it in a very ad hoc way. So what we mean is that we want to find a function so we can just predict the response from the feature vector, okay? Such that we want fxi to be close to yi for all the i's. That's our goal. So our supervised learning is to find this function. So therefore, you see that for supervised learning, we can always use yi and xi, our data, to help us find this f. So the most common loss function for finding such f, clearly you can see it will be the sum of the squared loss, right? We can do I from 1 to m, and we can do yi minus fxi. We take the difference and we take the square, because we don't care about the sign of the difference. So we just square it to remove the sign. And therefore, you see, to minimize this loss function, or to find f, becomes an optimization problem. We just want to find the f to minimize this. Okay, this is the common goal for all supervised learning algorithms. You may use different losses, then this may be different. For example, if your yi to yn are binary labels, that is something we call a classification problem. In that case, you may use, say, the cross entropy loss in machine learning, or some people may use the hinge loss as in support vector machine. But these are all variants of loss. But you can understand that ultimately the loss will be smaller if the fxi's are closer to yi's. So you know that trait. All right. So for the different model complexity, it's actually about the complexity of f. Okay. So model complexity, you can think of it as the number of parameters of f. In the function f, how many parameters do we need to specify this function? So when we say linear regression, or it can be called a linear model, the same thing. It's just that when we focus on the probabilistic part, we call it linear model. If we just focus on the algorithm part, we call it linear regression, but they are essentially the same thing. So this is about a linear f. F is linear in the P features. So what we mean is that we can write fxi. We know xi itself is a p-dimensional vector, so we can write out xi as xi1 to xip. Okay, so the p elements in the ith feature vector. So by linear function, we mean that the function is just a linear combination of the p features plus an intercept. So we can write it as beta 0 for the intercept and beta 1 times xi1 plus 2 beta p times xip. That is linear regression. Okay, but if we go for more complicated things, like if we say we are doing a tree-based regression, then this f is a tree. So by tree, we mean something like this. So you can divide the whole feature space into this. So let me just give you one simple example for, okay, let's say p equals 2. Okay, and we can call this the dimension 1. We can call this the dimension 2. So a tree can be reflected here graphically as if we think it's better to first divide my data into 2 halves based on dimension 1, so that I can use dimension 1 to distinguish the large yi's from the small yi's. So then I do a split here. And then within each half, so given that dimension 1 is on the left, I can further divide my dimension 2 as this. And then I can further divide my dimension 2 as this. So this will give me 4 squares. So probably what I can do is that for each xi that falls in 1 square, I'm going to predict it with 1 value. So that means here the prediction will be, I'm just making it up, 1, 2, 3, and 4. So what this means is that if xi is in this square, is in square 4, then I predict it's yi. Often we call it yi hat. So based on this f, xi is equal to 4. So this means that my predicted value will only have 4 values depending on how I define the tree. And of course, sometimes people can go to do the division again and again. So you can make the tree that becomes very complicated. This is what we call tree-based regression. And of course, if you have multiple trees and you want to ensemble the trees, then you will have random forest. So the tree-based regression and random forest, they are not linear functions. And neural network is more complicated. So you would have linear combination, and then you apply a nonlinear transformation to the combination to just construct new features. So like you originally have P feature to start with, you can combine these P features. So each linear combination of these features and a nonlinear transformation will give you a new feature. For example, you could do this for 100 times, you will get 100 new features. And starting from there, you can go to the next layer by having linear combination of the 100 new features plus a nonlinear transformation to get another new feature. So you can go that on and on. So what I mean here is that the neural network is nothing special. You can just think of a neural network. You can think of as a complex F function. Yeah, so it is a complex function. You are using that layers, the linear combination, and the nonlinear transformation to make the F really complicated. So yeah, so as you can see, when we talk about interpretability, it is essentially about the parameters of F, whether these parameters are interpretable or not. If they are not, then we say the model is interpretable, which is clearly the case for linear model. You can just look at beta 1, think of it as the effect of feature 1 on the response, beta P as the effect of feature P on the response. But for neural network, we do not have such a straightforward interpretation just based on the model parameters because it has so many parameters. But what we can do is that nowadays people have developed or approaches, very smart approaches for interpreting those. They call these black box. So when the function is too complicated, black box models. So I can share the link under our recording. So there is an online book called Interpretable Machine Learning, so which has included all the modern techniques for interpreting those black box algorithms. Okay, that's the overview. And if a function is doing very good job, you expect its loss to be very small. But please bear in mind that this is something we call training error, which means that you are using your data to find F. And you can imagine that if I don't have any test data for evaluating the performance of F for prediction, this is not meaningful because I could, if there's no constraint on the shape of F, I could just arbitrarily set Fxi equal to yi for every I. Then I will have zero training error. But such an F may not work well on test data. So you could imagine this case. For example, if I just have P equals 1, okay? So then this is my Xi, this is my Yi. So because the features are one-dimensional, can make a plot. So if your data looks like this, and if you just do that interpolation, so you do this, okay? So if you just connect the dots, you will have zero training error. But if you have other data that's not used for training and add them to the plot, then you will see for these new data, you're not going to predict well because you are basically fit a model just to your training data. And this phenomenon is called overfitting. So therefore, to avoid this issue, there are two approaches. One is to add a constraint on F so that F is simple and smooth. That's the simplest one is our linear model because a linear model would just fit a line through the points. And another approach is that you can, so this is by just restraining ourselves to a small class of model like linear model. Another possibility is that you can do some people call cross-validation. So cross-validation means that if you have just one set of data points, you need to specify or divide them into k folds. And each time you use k minus 1 folds for training and use the remaining 1 fold for validation. That's what the term cross-validation comes from. So then what does it mean? It means that let's say k equals 5. So I use 4/5 of data to train a model. I apply the trained model to the 1/5 data to calculate the error, the loss. Then I do that by in turn for every field will be left for validation for once. In the end, I am going to get k prediction errors. Okay? And I'm going to take the average and use the average as something we call the cross-validation error, CV error. So you see, we do this by fixing a model complexity. Let's just say that for a certain type of model, given a certain way of parameterize f, even though we set the parameters, we don't know their values, just like linear model. This is how I parameterize it with p plus 1 parameters, but I didn't know their values. So these values, beta 0, beta 1 to beta p, are going to be estimated from my training data. So therefore, you see, in the cross-validation, every time when I do training, the parameter values will be different from the next time. So I'm actually getting 5 model parameters, 5 sets of model parameters, and I get 5 prediction errors, I get a CV error. So this CV error is only for that model setup. It's not for a particular model with parameters given, because I still don't know the parameters. So usually, let me just give you one example. If you want to compare 2 models, one is just a linear model, and the other model is that you include interactions between 2 features. So that will suddenly increase my parameters to additional p choose 2, so many, because for every pair I can have an interaction, and that interaction needs a parameter. So to compare these 2 models, one with fewer parameters, one with more parameters, I can use cross-validation for each model. And then I can compare which one has smaller cross-validation error. And I pick that. For example, it is the linear model. Then I just settle down with linear model, and then I fit this linear model on my whole data set to obtain my final parameter estimate and my final model. So that's the whole idea. So you don't get a final model for predicting future data from cross-validation. You just get a model choice from cross-validation regarding the model complexity. Does that make sense? Okay.
Hi, Jessica. Do you think you could comment on like the information criteria?
Okay. So I think that's something very related to what we said in our t-SNE part. So that KL divergence is an information criteria. So it tries to measure the information in the density we calculate for pairwise data points in the low dimensional space we try to find, and densities in the high dimensional space we calculated. So that's just one way. So that KL divergence is a loss function. And I think, so coming back to here, so when we say that cross entropy loss, which I didn't write down, for the classification when yi is binary and your fxi's values are also binary. So when that happens, you're also trying to, the cross entropy is trying to compare, I think it's kind of like you're trying to compare 2 Bernoulli distributions. So for example, that means for your data, what you want to say is that given my feature vector xi, the corresponding yi is a Bernoulli variable, right? It follows Bernoulli with a certain probability. You want to evaluate whether this observed Bernoulli variable is close to your predicted Bernoulli variable in terms of their distribution. So that's why it is kind of like an information-based criteria. But still, no matter which one you choose, I think it's different motivations. But ultimately, these losses are going to force you to make the fxi close to yi. And some losses were proposed for computational reasons. For example, it's easier to optimize. And clearly, this is a very easy loss, the square loss, because we can take derivative very easily. Okay, does that answer your question?
Sorry, I meant more like referring to evaluating different models, like the Bayes information criterion and the
Oh,
tag.
you know, I see. I know what you mean. You mean the AIC or BIC? I see. Okay, yeah. So for that one, it is okay. Maybe I can say a little about that. So the AIC is earlier, and then BIC was proposed later. So I would say these approaches are particularly useful for the probabilistic models. So they are useful for probabilistic models so that you can write down a likelihood. So they rely on likelihood and the MLE, maximum likelihood estimates. So therefore, for the black box algorithms that you cannot write down the likelihood, you cannot use those approaches. And these were classical approaches that were so popular because they only requires fitting the model to your whole data for once. Okay, so they only require one fitting of each model to the whole training data. Okay, and what's the difference between those two things? These two things have their different assumptions and their different derivations. So AIC got a name because it is based on the information theory. So what it actually does is to address this issue. So let me talk about AIC first. So the issue is that when you do when you actually evaluate the density, okay, so the information in the joint data density. So let me see that here the data, I can say the data is f of x and y. I put them together. And this will depend on some parameter in the model that generates the data. Let's just call that f theta. Okay, so that's the theta is the model parameter for generating the data. But because this information, this is not calculable or it's not observable, we don't know what theta is. So instead, we actually use MLE, maximum likelihood approach, to find theta hat from the data, from my XY data. So let me just be more specific. So you can think of these data together, I call them just as X and Y. Y would just be stacking the Y1 to Yn as a vector. Okay, so this is the what we call the response vector. So for simplicity, I just call the data X and Y. So you see, the data is used for once to derive the MLE. Then you put the MLE into the density, and now you evaluate this thing, f, x, y, given the MLE theta hat. And so the motivation now comes in. So when you use this to evaluate the information, you are using the data for twice. The data is used for theta hat, and now the data is used again for evaluating this. So this causes some information loss. Loss due to the use of data for twice. So this is something you should be aware of. In any statistical procedure, if you use the data for twice, you must be very concerned about the result, about the validity of the result. This has the same flavor as overfitting, just to put it in a simple way. So therefore, the AIC was motivated to correct for this, to make a correction between these two things, to adjust for the fact that, okay, the data is used for twice, then what should I do? How should I make this thing, like this information, as a more accurate estimator for the information I'm really interested in? So it turns out that the AIC information, it becomes, the correction term can be approximated by 2 times the number of model parameters. So in other words, the more parameters theta contains, or like theta, let's say p-dimensional, contains the p parameters, the more parameter theta contains, the more information you lose during this overuse of the data for twice. So that's the motivation of AIC. So that's why the AIC criterion is just like 2 times the log likelihood minus 2 times the number of parameters. So that what you want is that you want to maximize the likelihood by picking models, right? Each model has its own maximum likelihood. And it is no surprise that the larger the model, the larger the likelihood. Because the likelihood, what it describes is how well your model fit to your data. Clearly, the more complex the model is, the better it fits to your data. So the likelihood always increases as model complexity increases, as long as you use the MLE. So maybe I just put it into words. So what I mean is that if you have 2 models, so let's say, probably if you compare these two, okay, so theta 1 corresponds to 1 model by restricting some parameters to 0. Let's just say I have the first parameter beta 0 set to 0, and I just have beta 1 to beta p. That's theta 1. And then for theta 2, I do not have this constraint. I can allow every parameter to vary freely. So clearly theta 2 corresponds to our more complex model. And I do MLE under each. Try to fit the data, find the MLE. So I got theta 1 hat and theta 2 hat. So it will not be surprised that if you just compare the log likelihood, I wrote it as log L theta 1 hat, and I write L theta 2 hat. So there's no surprise that this one will always be bigger because you have one more free parameter to fit your data. But what AIC tries to do is that it doesn't want you to always go for the bigger model driven by the likelihood. So it does the correction. So AIC is 2 times the log likelihood of theta 1 hat minus 2 times the number of parameters. Here is p, okay? And over here, it's 2 times the log likelihood of the MLE here, minus 2 times p plus 1. Now we have one more parameter here. So that gives you minus 2. Then you're going to compare these two to see which one is bigger. Now it's not necessarily you have this side bigger because probably the difference in the likelihood is not bigger than 1. Then you will stay with the simpler model. So that's the AIC. And then you can see you are just fitting each model setup for once to your whole data, unlike in cross-validation. So given cross-validation, given the 2 model setups, you are going to fit each for k times to evaluate the CV error. And once you pick the model, then you're going to fit the chosen model again to the whole data set. So clearly that's more computationally intensive. So that's why in the old days, the AIC is a very popular way of doing this correction, model selection. But of course, it relies on that information theory, and also it relies on a lot of, I would say, very brave assumptions during the calculation so that you can get this very simple formula. And BIC, the name stands for Bayesian, Bayesian information theory. So this one has a Bayesian perspective. I just say that. And it has some Gaussian approximation in its calculation. So that's why in BIC, I'll skip the technical details. If you're interested, probably I can invite you to listen to my other class, 205. So usually I'll talk about these in detail in my last lecture, if time permits, but I'm not sure about this year. So we'll see how it goes. But for BIC, this constant becomes minus log n. So it's not 2. And here it becomes log m. So clearly you see that you're putting a heavier penalty on the number of parameters. So compared to AIC, BIC will tend to select a smaller model. In terms of model complexity, it's more conservative. Okay, and later people have some discussion about whether to use AIC or BIC, but probably I'll stop here. Yeah, I think they're both used, but I think previously, and they have different theoretical properties under different assumptions. So I wouldn't say which one is necessarily better than another, but they are both commonly used criteria. So this can also show you the case that the fact that model selection itself is quite arbitrary. It depends on the person who does the data analysis. Okay, so does that answer your question? Okay, great. Okay, now let's move back to the linear model. The simple model we want to talk about. It is so widely used in genetics, I would say. Statistical genetics is the place where linear model is predominant. So linear model, I give you this already, right? This is the formulation. So we have a linear function that combines the features for prediction. And so here we are going to be more specific. If we're going to write down this model as a probabilistic model, so we can write down likelihood, we need distribution assumption. So this is often called the normal linear model. So what we assume is that for each yi, and so for each yi, we assume that it is a linear combination beta 0 plus beta 1 xi1 plus 2 beta p xip plus an error term epsilon I. So this error term is something I assume that, okay, my data is not perfect. I do not assume yi is just equal to this linear function. There is some random error. So the normal linear model means that the random errors are IID, identically independent and identically distributed as a normal variable with mean 0 and the common variance sigma squared. Okay, that's the normal linear model. So now we can actually make this in a more matrix form so that if I define this xi vector by putting the intercept, include intercept into it, 1 xi1 to xip. Okay, if I do that, and if I also stack the beta into a vector, beta 0, beta 1 to beta p. If I do this, then essentially you see this term can be written as an inner product of these two vectors. So yi can be written as xi transpose beta plus epsilon I. So the same thing, just a vector form. And this is what we often write in linear model. And what's even important to consider the normal linear model is that we can actually decompose this into a two-layer or two-part structure. We call this the random structure. So if some of you are in my other class, we have been talking about this for the whole quarter. So the random structure is assuming the distribution of yi. So given this, we can say, okay, if we denote, say, expectation of yi, we give it a notation mu I. This will help us a lot. So with this notation, we can write yi as normal variable IID, independent. Now you can go to this independent with mean mu I and the common variance sigma squared. So you see, this is a natural result from this random error assumption, right? This error is normal. So putting it here, I'm just shifting yi by this quantity. And here it is just xi transpose beta. So I'm actually having yi distributed around mu I with variance sigma squared. And then the second part is the systematic structure. This is about how I am going to model mu I, the expectation of yi. So in the linear model, mu I is just modeled as xi transpose beta. So in other words, a linear function of my predictors will give me the expectation of yi. And yi follows around its expectation with this variance sigma squared. This is what we call normal linear model. And then, because what we're most interested in is the beta coefficient. Then with this random structure and systematic structure, we are going to write the likelihood of beta and sigma square, right? And then we do MLE. Maximum likelihood estimation to obtain beta hat, sigma square hat. We're done. So fitting the normal linear model by MLE, by coincidence, happens to be just the least square formula. Yeah, the least square regression gives us the MLE for beta hat. So that's something very interesting. And we actually have that least square formula back in the era of Gauss. So that's the time when we don't even have the definition of likelihood, those kind of statistical concepts. But that procedure has been there for a long time, just as PCA. As a mathematical procedure, it has been there for a long time. But our statistical interpretation based on the randomness, how we assume the distribution, and how we write down likelihood, these are more recent in the past century. Okay, that's the linear model. So now the GLM, we're going to move on to generalization. So generalized linear model is to deal with the case where your response is clearly not Gaussian, right? So you see this random structure tell me the yi's are drawn from a Gaussian distribution, normal distribution. Then you can expect the values of y. What should it be like? It should be real values, right? It should be real values and it should be continuous. And so and its range is not constrained to a certain interval, it can be very negative, it can be very positive. That's everything you want to expect for yi being normal. But the generalized linear model can allow your yi to be of other forms. So for example, in the logistic regression, it's a very popular type of GLM. In logistic regression, your random structure, the yi itself is binary. So if y is binary, then the most natural thing to assume that it is a Bernoulli variable. And this Bernoulli variable, the parameter of the Bernoulli is just the mean of yi, right? So I call that mu I. That's just the definition of Bernoulli. And then it becomes the question of how to link this mu I to my predictors, to my features, the xi1 to xip. How do I do that? So for this part, systematic structure, we need to think about the range of mu I. So as a Bernoulli variable, this Bernoulli parameter, this mu I is actually between 0 and 1. That's what we know. So how can we link this to xi transpose beta? So the parameter, the beta has no constraint. Also, my predictors has the features has no constraint. So this is actually real value. While the mu I is constrained between 0 and 1. So here's the idea. So you can see that by doing this, mu I divided by 1 minus mu I could actually make the range from 0 to 1 to 0 to positive infinity. Because you can see whenever mu I is getting close to 1, this denominator is going down to 0. So this ratio is going up to positive infinity. So and now I have 0 to positive infinity, but the negative range I haven't covered yet. So log can help me solve this issue. So by taking a log, I can cover the whole range from negative infinity to positive infinity. So in fact, what this is like, this is what we call the logit function. Okay, so some people just write it as logit mu I. And that's how we got the name logistic regression. So essentially, this logit function has the form like this. So if I just plot it, so 0's here, 1 is here, say 0's here. So what it look like is, so when I go from 0, and this is like mu I, this is logit mu I. So what happens is that when I go from 0 to go from 0.5 to 1, it will go up like this, but it will never reach 1. It will never touch 1 on the right hand side, and it will go down to negative infinity like this, but it will never touch 0 on the left hand side. So this transformation is monotone and increasing. So a larger mu I give you a larger mu I. You keep the monotonicity, but on the other hand, you just enlarge the region from 0 to 1 to the whole real line. So that's the magic of this systematic structure. So in other words, this logistic regression allows you to predict yi, which is binary, but yeah, it is binary, and it still can allow you to use this linear function to decide how each feature affects mu I. Because you can see that the larger this part, the larger the corresponding mu I. So I can write this equivalently as mu I equal to exponential function of xi transpose beta divided by 1 plus exponential function xi transpose beta. So this part being larger, this whole mu I is going larger. So you still have that effect. Okay, this is the logistic regression for predicting binary responses. And logistic regression is still very popular as a method for doing classification, not just for interpretability, but it's also very useful for classification, for prediction. Okay, so again, you can write down the likelihood. So here the likelihood is only about beta. We only have that parameter. And then you do MLE to maximize the likelihood to obtain beta hat. Okay, and then with beta hat, you are going to predict. Sorry, I didn't finish this part. So with the MLE in the linear model, you are going to predict yi hat just as xi transpose beta hat. You use this beta in place of beta hat to do the prediction. And then in the logistic regression, you are going to predict. So if you want to do yi hat to make it as binary, so you are going to use this mu I prediction, so which is exponential xi transpose beta hat divided by 1 plus exponential xi transpose beta hat. So this is something between 0 and 1. It's not exactly 1 or 0. So then you need a truncation. So for example, many people say use an indicator function. If this predicted mu I hat is greater than 1/2, I would predict yi hat equal to 1. Otherwise, I will predict 0. So you do a truncation here. Okay, that's the logistic regression. And another one that's very popular is something we call the Poisson regression. So again, we just look at the random structure and we look at the systematic structure. For the random structure part, now Poisson is for the case where your responses are counts. Okay, so this is for yi being 0, 1. And Poisson are counts without a clear upper limit. So it seems that the counts can be very, very large. So in this case, Poisson is a very common distribution for modeling counts. So you can just assume yi follows Poisson with mean mu I. So here the constraint on the mean is that the mu I must be positive. And then systematic structure is how we are going to link this mu I to our linear function of features. So you see this this xi transpose beta is real valued while mu I is positive values, right? So to make their range match, again, we do transformation on mu I by taking the log. So log mu I can make its range from negative infinity to positive infinity. Then we assume log mu I as xi transpose beta. Okay, so one thing I didn't say, because I think it's a jargon, so if you don't know it, that's fine, is that in the GLM, people call these transformation on the mu I, here the logic function, here the log function, as the link function. That's a jargon used in GLM. It's just about how you are going to transform the mean of yi so that after transformation, it can be written as a linear function of your features. Okay, so these are link functions. So again, given Poisson regression, you are going to do likelihood of beta, and you do MLE to obtain beta hat, and then finally you do prediction. So here, how is your prediction? So you are going to predict based on this mu I hat, right? So given that, so you are going to have exponential, so mu I hat is equal to exponential xi transpose beta. So you are going to do exponential xi transpose beta. So you could predict yi hat in this way, but this is not guaranteed to be an integer, or you can round it up so that your predicted counts are counts instead of integers. So either way, depending on your needs. That's the, oh sorry, beta hat. So that's the Poisson regression. And now you can see when I tell you, when I ask you what is negative binomial regression, based on the negative binomial distribution we discussed before, we know that it is over dispersion compared to Poisson, right? In negative binomial, the variance could be bigger than the mean, while in Poisson, these two must be equal to each other. So negative binomial regression, it is very similar to Poisson by just changing the random structure. So now the random structure becomes yi follows a negative binomial distribution with mean mu I, and we also need a variance parameter for the MB. But usually people just use a dispersion parameter phi and assume that to be common for all the observations, just as what we have for the linear model. You see that we assume each response to have its own mean mu I, but all the responses share the same variance sigma squared. So that can reduce the number of parameters. And here is the same. They share the same dispersion, but they have different means. And the systematic structure is the same as Poisson, because here the mu I is also positive. So to make its range matched with a linear function of features, we do log transformation. Okay, and everything follows. So that's MB regression. So everything in the GLM amounts to MLE for the parameter estimation step. And as long as you can estimate the model parameters, you can do prediction. And the prediction is based on mu I hat, because mu I is the expectation of yi. So it makes sense for you to predict yi by its expectation. But because you don't know its actual true expression, you have to estimate its expectation. So that's mu I hat. So the common theme, so let me just summarize, is that the summary is that you go from data with the model, you do the MLE to obtain the beta hat, and then based on the systematic structure you have in your model, you are going to find mu I hat, okay, based on the beta hat. Because the systematic structure is just about the relationship between mu I and xi transpose, and they share the same common beta. So beta is applied to every observation. And then you get mu I hat. And then this is how you're going to predict. Use for prediction. Okay, and one thing I want to add is for logistic regression is that we talk about logistic regression for binary responses, but this can be more general for, I would say, two category count data. So a generalization is what we call binomial logistic regression. And we often say that this is for group data. So what, sorry, I didn't show it. So what does this mean? This means that your yi is more reasonably to be assumed as following a binomial regression with a total ni, okay, and a probability parameter pi I. So in this case, the mu I will be equal to ni times pi I. So in what case do you want to do this? That is when you have several Bernoulli or binary responses, they share the same feature vector. So for example, if I have people in different regions and my feature vector is only specific to region. So in other words, people in the same region share the same feature vectors. So their xi's are all the same. So in this case, it does not make sense or it is not computationally efficient to keep those people's records if their feature vectors are all the same. So then what we do is that we just combine those people. So let's say if we combine ni people, we just take the sum of their binary responses. That total is called yi. Let's say ni equals 100, and out of the 100 people, 50 are yes. So then this yi is equal to 50. So we know that the sum of Bernoulli variables with the same probability would be equal to a binomial random variable, right, with the same probability. So that's how we group the data. And so with this, then you can have the systematic structure as the logit pi I. This is from negative infinity to positive infinity equal to xi transpose beta, and you're done. So systematic structure stays, it's just that after grouping, your data's random structure, your model's random structure become binomial instead of Bernoulli. And so you may wonder, when should I choose binomial logistic regression versus Poisson regression or MB regression? So these two are clearly competitors. They are for the same purpose. But binomial data is a little different. Although the data count can vary from 0 to ni, but you know there's an upper limit there. You know it cannot go beyond ni. So that's the case where you will use binomial logistic regression. But if you don't know any upper limit in your counts, then you should go for Poisson regression or negative binomial regression, depending on which one fits your data better. Okay, so that's the GLM. That's a very short introduction of generalized linear model. So unlike my other class, we spent like 4 weeks talk about this only. So this is a very short introduction, but I think this can help you at least know a little bit about what it is doing. So now let's come back to DESeq2. So DESeq2 is talking about what? So in DESeq2, what you basically have, okay, what you basically have is one of your predictor or feature here, let's say xi1, is the condition. So it is a condition 1 or condition 2. So it's a categorical feature. And then let's say feature 1 is the condition. Then what you do is you look at its corresponding beta 1. So DESeq2 is testing whether beta 1 is 0 or not. So for that question, we can use the existing statistical test for generalized linear model. So if in the R, if you do the use the GLM function, then it will return coefficient estimates as MLEs. It will also do the statistical testing for each coefficient and tell you whether it's 0 or not. So that's how you're going to tell whether this gene is differentially expressed or not. And in DESeq2, they use negative binomial regression because their response are gene counts, read counts. So it makes sense to use a count-based regression. And because we know that negative binomial fits data better than Poisson does, they use that. An advantage of using the NB regression is also in the fact that you can incorporate other covariates you want to adjust for, like sample sizes and some other condition covariates which can influence this gene expression, but it's not related to the condition, treatment control condition of your interest. So you can always put those covariates, which you call confounders, that you want to adjust for as additional features into your model. So GLM will naturally serve the purpose of regressing out those things, because beta 1 is interpreted as the conditional effect. That is the effect of this condition predictor, this condition feature treatment control, given the existence of all the other features. So that's why this GLM framework is very useful for those type of differential analysis. Okay, so I think I'm going to stop here for today. In the beginning of our next lecture, I'll talk about the linear mixed effect models, what we use in genetics. So for the rest of today's lecture, I invited my PhD student, Xinzhou, here to share a nice example he has composed for showing you guys an actual application of the negative binomial regression and what we call the multinomial logistic regression. So Xinzhou, maybe you can start sharing your screen.
Okay. Can you see my screen now?
Yes.
Okay. So thanks, Jessica, for inviting me to give this brief introduction to these two regression models, the multinomial logistic regression and negative binomial regression. So today I'd like to show an example which is motivated by my research project. And originally it was about some data set, some biological data set, but here as the background was too complicated, so I changed this example into a food choice example. So here, the data set is about children's food choice. So as we know, children's food choice is influenced by different factors, including age, gender, and family income. And different food choices can be categorized. For example, we can categorize the food into fast food, healthy food, vegan. And if we summarize the food choices of the children within a month, for example, 30 days, then we can have a data set that looks like this. So here, the first 4 columns are the covariance of the children, including their age, gender, and income. And also, we have some columns which are about the summarized food choice of these children. So here we categorize the food choice within a month into 4 categories: fast food, healthy food, vegan, and none. So here, as we can see, each row of the data set, if we only look at the last 4 columns, the sum of these values will be 30, which will be the number of days in a month. So this is our data set, and from this data set, we want to infer whether the food choice are affected by these covariants: age, gender, and family income. So if there is a connection, that may be something interesting, and then we can use some generalized linear models to solve this problem. The first model, I think Jessica has given a brief introduction, which is negative binomial regression. In the negative binomial regression, the predictors are the covariants, including age, gender, and family income, these 3 predictors. And we will look at each category of food choice one by one. So for example, we can first look at the fast food category and make it the first response. So one thing to notice is that for negative binomial regression, there will be no limit for the count values of the response. However, in this example, the number should be this equal than 30, which means that it is not so appropriate to use negative binomial regression. But here I just make it an example. So for negative binomial regression, we look at one category at a time, and the model is as follows. So first, if we call this y, and we call the number of fast foods child I follows negative binomial distribution with mean mu I and dispersion parameter alpha, where mu I can be further modeled using this formula, so which is a linear combination of the predictors. So this is a model for the negative binomial regression. And after we fit the first response, fast food, we can further go to the second response, healthy food, and then vegan, and then none. After finishing all these models, the conclusion we can get from the negative binomial regression is, for example, whether age is related to the choice of fast food, or whether gender is related to the choice of healthy food. So we cannot give any conclusions generally for all the food choices, but we can focus on one category of food. This is the negative binomial regression. And for the multinomial logistic, sorry.
Xinzhou, maybe you can pause this here a little. Since Xinzhou just raised the point that he said the upper limit for each count of fast food cannot be greater than 30 because we have that 30 days per month. Then based on what I just said, what regression would be more appropriate here for this particular case if we consider that upper limit? Yeah, if you want to volunteer, just unmute yourself.
This seems like multinomial data, right? Or am I?
Yeah, this is the binomial one I just talked about. If you just want to say, if I want to compare fast food versus the rest, then the fast food count is going to be drawn from a binomial distribution with ni equal to 30, total is 30, and the probability. So you're going to use that. So that question will become, okay, does these age, gender, income have any influence on people's food choice between fast food over others? So that would be the question you can answer with a negative binomial regression. But Xinzhou here, he just pretend that, okay, this is not a choice. It's just like how many fast food a person has per month. And if we pretend that there's no 30 there's no upper limit as 30, then you could model those counts using a negative binomial distribution, and then you could actually answer this question Xinzhou just said. That is, do those predictors have any influence on the amount of fast food a person takes per month? So it becomes that question. So it's not fast food versus the rest, but just the fast food itself. Yeah. So I hope this clarifies. And Xinzhou, please continue with the next part.
Well, actually, quick question about that. Sorry. If none is an option, which wasn't it in the table, then excluding that column, does that eliminate that issue or no?
No, because still you always have that total with under 30 anyway. Yeah.
Thank you.
Okay. Thank you.
Okay, that's for the negative binomial regression, and the next model is multinomial logistic regression. So I'm not sure whether Jessica has introduced logistic regression in this course, but yeah, this is very similar. Okay.
Just now, we're talking about binomial. So I talked about binomial logistic regression. So here you are talking about multinomial logistic regression. Yeah.
The difference between binomial logistic regression and multinomial logistic regression is that in multinomial logistic regression, we have multiple categories. So in binomial, you only have two categories. So the response will be 0 or 1 if for a single output, or if it can be counts for the two groups if for group logistic regression. So here we can make the response all the 4 categories of the food in the multinomial logistic regression, all these 4 categories, and we can look at all categories at the same time. In the negative binomial regression, we model the counts. So we focus on these count values, but in multinomial logistic regression, we focus on the proportion of each category. And the random structure for the multinomial logistic regression is as follows. So if we use fi to denote the food choice for the ith child, then we have this model. The probability that food choice of child I is vegan over the probability that this child choose fast food is expressed using this exponential of the linear combination of all the predictors. And then we can also have very similar formula for other categories. For example, healthy food over fast food, and we can also have none over fast food. So we have something, we can have a fixed category in the denominator so that we will have 3 such formulas. And then with these 3 formulas, we can get the probability for each of the categories. And then the probability, and then the whole vector for each child, for example, for the first child, the response will be 10, 10, 10. This 10, 10, 10, 0. This vector follows a multinomial distribution with 4 elements and which sum up to 30, and the probability for each category will be this from this formula. So that this will be the statistical or random structure of the multinomial logistic regression. So generally, we can answer from the multinomial logistic regression, we can answer the question whether a covariate, for example, age, is related to the proportion of all the categories. So we can see from multinomial logistic regression, we can answer more general question. We can look at all the proportions of categories at the same time. So this is the difference between multinomial logistic regression and the negative binomial regression, although they can also work for count data, but they have different meanings or statistical questions to answer. So this is their difference. And if you want to implement these 2 kinds of regression models in R, so here are the packages and functions for these 2 regression models. For the negative binomial regression, we use the package mass, and we use a function called GLM.NB. And we can see the formula for this function is very, very similar very similar as the LM function or GLM function in R. And for the multinomial logistic regression, we use a package called nnet, and the formula for the multinomial regression is also very similar to the previous one. And the only difference is that the category or the response can have multiple columns. So this is the 2 models. And do we have any questions?
And also, I didn't mention this in my lecture, but Xinzhou, if you go to your last slide, for implementing the GLM for not negative binomial, but just like the GLM for binomial regression, binomial logistic regression, or the binary version, the logistic regression or Poisson regression, you just need to use the GLM function in R. So that GLM function includes all those things. You need to specify family based on the random structure, either it's Poisson or Bernoulli or binomial, and you need to specify the link function. But if you don't specify the link, it will use the default link function for each family. Yeah, so if you want to play with that, there are several examples in the R help page, so you can try the examples over there. And I want to say that Xinzhou was motivated to do this because we were approached by a collaborator who found that existing bioinformatics packages didn't solve their problem. So then we found, okay, probably the problem is quite straightforward. It is. I think we can just formulate this as a simple negative binomial and multinomial logistic regression problem. So that's how we approached it. So I think the take-home message is that sometimes you don't need to really rely on some tools you don't fully understand. And some problems are not as difficult as it seems in biomedical research, in biomedical data science, I would say. Okay, so any questions for Xinzhou before we finish today's lecture? Okay, so the plan for next lecture is that I'll try to quickly go over the linear mixed effect model part, and then we will talk about some interesting association measures between two variables. And as I said in the beginning, if you didn't sign up for the group project, please do so as soon as possible. So for the slide, okay, so Xinzhou, you can share the slides, your slides with me, right? I can post them to CCLE. And as you know, we always share the recording, so you can also see the slides there. Okay. Okay, thank you very much, Xinzhou, for your guest tutor.
Thank you.
Thank you. Okay, thank you. Thanks, everyone. That's all for today. Bye. Bye.